everyone. I'm very disappointed not to be with you in person in the room today. I had hoped to travel up and be with you yesterday and this morning, but circumstances of the weekend conspired to prevent that. There is someone in the room who will be talking in this session, though. I'm co-hosting this, co-presenting this with Abigal Waring, and she'll be doing the Cryosphere part of the talk, and I'm going to be talking about the inland waters part. This is the outline of what we're going to cover. I'll try not to delay you any more, and Abigail will be doing the last 15 minutes or so of this talk. So, into thermal remote sensing of water in general, and then focusing mainly on inland waters and also coastal zones in the course of this presentation. So one thing to comment at the start is that surface water temperatures are actually the most accurately measured temperatures from space. So if you're measuring the sea surface temperature in the open ocean, accuracies are quite commonly of order a third of a degree or less. And in inland waters, the accuracies can be also very good, half a degree or 6/10 of a degree or so. And you might wonder what the reason of those relatively small uncertainties are. It's because we're dealing with a much less complex surface, especially if you have a situation like the picture on the left here, where we have nice calm day and a very smooth surface. This water surface has pretty well defined properties, and of course it has a very simple geometry. And so quite basic laboratory measurements can tell us a lot about the emissivity of such a water surface under calm conditions. It's basically driven by the intrinsic properties of water, and therefore amenable to quite simple physics. Of course, it becomes a little bit more complicated if the surface is roughened by the wind, but even then, there are models of the effective emissivity of water surfaces that take into account the main factors that are predictable if we have some knowledge of this, either the surface state or the wind. So those are the satellite view angle, the degree of roughening under windy conditions, and also salinity and temperature. The dependence on all those factors of emissivity of the water surface is quite well modeled and understood. We also are in a fairly advantageous position in that we understand the definition of what we're measuring. So there's much less definitional uncertainty when we're looking at a water surface than some of the other surfaces you've been talking about. The radiance from a water surface comes from a thin of order 10 micrometer layer at the top of the water, and that's called the skin layer. And although it's different to temperatures we might be interested in below that skin layer in the main body of the water, those relationships are pretty well understood as well, and pretty well able to be modeled. I just show you this movie on the left. I'll show you it first. And now I'll explain what we're looking at, and I'll show you again. That was an infrared camera observation of a water surface up close from a boat. It was dark to start with. Dark is cool in this movie. And then you saw little black dots appear, and those were raindrops being caught in flight as they fell to the surface. When those raindrops hit the surface, they were disrupting this skin layer, so that the skin layer had a certain temperature drop across it. So the top of the water at the interface was a bit cooler with warmer water underneath. The rain droplets disrupted that, and then we started seeing these brighter temperatures coming from underneath. So that's what's going on. Let's play it again. And that's the disruption of the skin layer and the exposure of the warmer temperature underneath the skin. As well as the skin effect, During the day, if the sunlight is very strong and the winds are relatively calm, there can be a diurnal layer that forms at the top of a water column, just a few meters deep, that is warmer than the water below. But if it's windy, the wind will tend to keep mixing the heating of the surface by the sun down, and you won't get that forming. So we have, and again, that is also something that people model quite successfully. So we have a very well-defined measurand and the ability to transform between different types of near-surface temperature through modeling. Now, the skin surface water temperature is actually what you want for some applications, because it is the temperature that's most relevant to certain interactions of the water surface and the atmosphere. So if you're more in the meteorological end of the spectrum, the skin is often what you want. It affects the energy balance directly. It's what drives the evaporation and couples to the atmospheric boundary layer. But temperatures below that skin and sort of more through the depth of a water column are more relevant to some other applications, particularly when it comes to thinking about ecosystems and water quality impacts, such as species that are sensitive to temperature. And also a concept that I'll be talking a fair bit about, which is mixing regime, particularly relevant to lakes, and essentially lakes that don't mix all the way down to the bottom of their depth can end up with low oxygen levels in the bottom of a lake, and that has a big ecosystem impact. So to unpack that a little bit more, here is a schematic of, this is based on Lake Malawi, in fact, which is a very deep lake. Obviously, it's in the continent of Africa. And we have here a schematic of the temperature with depth at different times of year. It has a winter season, which is cool, dry, and windy, when the temperature at the surface is not so different from the deep lake temperature, maybe degree warming. Sometimes if it's cool enough, windy enough, that difference will erode away completely, and therefore occasionally a lake like this will mix because there's no buoyancy inhibiting mixing of the upper and lower waters. So when that temperature profile arrays to be essentially isothermal, a lake like this will mix. But that's relatively unusual in this particular lake. It's a warm, irregularly mixing lake. And then in summer, when there is more insolation, less wind, that difference between the surface and deep temperature becomes more pronounced. The warm layer is a bit shallower, and the region over which the temperatures are changing, the thermocline, becomes a bit deeper. And this is a much more stable situation. It's more difficult for the wind to mix that warm surface water down because of the buoyancy differences associated with temperature. So that's a warm lake. Bear in mind that in an inland water body, the minimum, the maximum density of water occurs not with the coldest water, but actually around about 4 degrees, and that's quite important for lakes in other climates. We'll come back to that point in a second. In terms of the usefulness of thermal remote sensing for looking at lakes, it's surprisingly difficult to source in situ measurements of lakes temperatures around the world. We've done this over many years, collected a lot of data over many years. If you want to go back multiple decades, there are more or less 5 time series, certainly that we could find, that tell you how lake temperatures have changed over time. And that's on the left. And then even with slightly shorter records, looking at lake temperatures over the last 2 or 3 decades, we are involved at Reading with the annual State of the Climate reports. We quite often do a section on lake surface water temperature change. And the plot on the right, the in situ lake temperature anomalies, plot there was represents all the lakes we could find time series for over just a couple of decades from around the world, from in situ measurements, whereas the upper panel represented a selection of lakes that we observed by remote sensing over that period. And so we've done a fair amount of looking at lake surface water temperatures from the point of view of the lake-climate interaction over time. And on a global scale, you can only really do that by remote sensing because of the relative lack of in situ observations. But the surface water temperature isn't necessarily the only thing we want. As we've seen, there's a complicated lake temperature profile, and we really like to be able to say something about that for lakes around the world. And so one approach that's worked and given us quite a lot of insight is to use the time series of lake surface water temperatures as a modeling constraint. There are various models that can be used to simulate lakes. We've been using a one-dimensional model called F-Lake or Flake. Others are available. And there are a number of parameters in such, if you set it up for a particular lake, there are a number of parameters you have to choose carefully to represent that lake. Things such as the general opacity of the lake, which varies from water body to water body. That affects how deep the sunlight incident on the lake gets. And that, of course, affects the distribution of heating in the vertical. The translation between a numerical weather prediction model's value of wind at a lake and the wind that the lake actually experiences at its surface is not one-to-one, and therefore there's a wind scaling parameter that could account for things like fetch across the lake. The depth matters, especially if the depth is shallower than the sunlight penetrates down to. That's a parameter that isn't always known, but is an important one in determining the heat balance of a lake. And then if there is seasonally covered ice, then the albedo of that ice makes a difference to the disappearance of the ice in the spring, and that also is a factor that can be tuned. So doubtless there are other factors one could choose to tune, but we did a lot of working just on those four and learning how to use time series to tune those parameters such that Flake well captured the surface temperature evolution. So that's shown in a couple of examples on the left. And the idea is, the concept is that if we can find a way of modeling the lake with this amount of fidelity in terms of annual cycle, in terms of the interannual variability, all of which you see are quite well captured here, then the model is doing something informative about the lake throughout its whole profile that's being modeled. And that is an assumption, of course, but it's more information than is available for nearly every lake around the world in terms of temperature profile. So the first case study I'm going to look at looks at that technique in terms of looking at the worldwide changes in lakes in interaction with climate. And there are lots of ways in which climate change can take lakes. In view of time, I'm not going to dwell on what they are too closely, but just a couple of examples. You can imagine, for example, that if the ambient air temperature above a lake changes, warms up, then that tends to change the equilibrium temperature of the lake as well. And things like sunlight changes, wind changes, all those climatic factors can have an impact on lakes over time. Now, I mentioned that this characteristic of mixing, and we saw the seasonal cycle of Malawi in that earlier schematic. When we're looking at temperate lakes, many of them are dimictic, which means that they mix during 2 seasons of the year. They mix in the spring when cold water less than 4 degrees begins to warm up, and at 4 degrees the whole water body can mix. Previously to that, the surface layers have been cooler and therefore less dense, and floating on top of deeper layers that tend to be around about 4 degrees. And when it all equalizes, the wind can mix the entire depth of the lake, taking oxygen down and having a big impact on the lake ecology. Then as summer progresses, the top layers of the lake tend to get warmed by the sun preferentially, because the top layers trap the sunlight close to the surface. And we get this warm layer that tends to strengthen over the course of the summer. When the lake begins to cool down again in winter, the temperature starts dropping again. At some point, it will get close to 4 degrees, and the wind will be sufficient again to mix the whole depth potentially. So this is one of the types of mixing regime that exists in a lake. There are many, as you'll see in a minute, and I'm not going to go through defining them all, but this is quite a classic type of lake mixing regime. And it has very specific ecological impacts. And so the change of mixing regime that lakes might be subject to under climate change is very important. So we did a study on global lakes looking at their mixing regime using lake surface water temperature in the current day, because you can see the signature of those changes in the lake surface water temperature of those mixing events, for example. And then using projections of future climate, assessing which lakes would change in their mixing regime. And the rather dramatic, I mean, there are, you can see here that the consequence of that study was a description of which are the most prevalent changes in mixing regime that we can expect under climate change around the world. The physics world take on this was that lake dead zones will kill fish and poison drinking water. But that's talking about the case where a lake that previously mixed basically stops mixing, and we get deoxygenation at the bottom of the lake. And it does have consequences such as that. Second case study. Now we're going to the coastal zones of the oceans, something completely different. And I thought I would just show this because it's an industrial case study, and this can also be done for inland rivers if they're sufficiently wide. So this was some work we did where we were mapping the discharges from a power station. Power stations and other industrial facilities that discharge cooling water have permits as to how much they can warm up or discharge into at their ambient waters. So just to show you what we're talking about, this is Heysham 2 nuclear power stations, and you can see these outflows into the North Sea, into the Celtic Sea, and these are the cooling waters emerging from the power stations. And there are permits associated with how hot those waters can be and what impact they can have on the environment. And EDF was interested in mapping out what's actually happening as a result of these warm water discharges. So I'll skip that. The outcome was essentially that the impact of the power station on the local water temperatures is tidally dependent, as you might expect. In the situation of the ebb tide, the distribution of warm waters above a certain threshold, the probability of that is shown in the map on the right, flowing away from the coast. More impactful on ecosystems was probably the flood tide, when the warm water is over a shallower set of sandbanks and mudflats, and therefore we showed through some hydrodynamic modelling that in fact the entire depth of that water column at times was warmer, and this information could be used in assessing whether or the extent to which EDF were staying within their compliance regime for these discharges. Similar analyses are possible at other locations. Third case study is I've included because it's quite a different way of looking at wetlands than the sort of direct observation of lakes that I've been talking about. So the Sud wetlands are in Africa and South Sudan, and the population there in recent years has been under a lot of stress and migration pressure through high levels of flooding. But this is not a situation where it's very easy to see which areas are flooded. So the monitoring of this has presented a significant challenge. And you can see the reason for this in this picture taken from an aeroplane flying over this region during a flood event. The flooding is underneath a lot of the vegetation. And so the usual ways of spectrally distinguishing water from vegetation get significantly compromised by this situation. Essentially, it just looks like wet vegetation rather than a landscape that's actually flooded. And so the way in which the World Food Programme has been assessing the flood extent is to use thermal remote sensing rather than the visible normalized difference type indices that are usually used for detecting water or vegetation. So over a 10-day period, what they do is look at the maximum and minimum land surface temperature. That's what it's called. But in a flooded area, of course, it's some sort of vegetation and water temperature. But the point is that when an area that was not flooded becomes flooded, that daily temperature range reduces significantly in amplitude. And that signature can be used to map out the flooded areas over a 10-day period. And this has been used very successfully. This animation is an animation of the result of this diurnal temperature range based method for looking at flood extent. So totally different way of using remote sensing to look at hydrology. Then the fourth case study I'm going to show you, which segues into Abby's presentation on Cryosphere thermal remote sensing, is a study where we're basically looking at the lakes around the periphery of the Greenland ice sheet in Greenland at a basic exploration level, really not there being very limited information about how these lakes behave on an annual or interannual basis. Using lake temperature data from the Climate Change Initiative project for lakes, which we're involved in, we selected 6 lakes labeled with letters in this landscape. You can see that there are Greenland, the area of Greenland is studied with all sorts of different lakes, different sizes. In the CCI, we're using meteorological satellites, so we're only able to look at relatively large lakes that are at least a couple of kilometers across. And those are the 4 labeled there. Another thing you can really see is that these lakes can be very different to each other, not least in their albedo. And that's to do with the existence of glacial flour in the lake from the grinding actions of glaciers or not. So the dark lakes are very clean, probably rain-fed and groundwater-fed, whereas the bright lakes, like Lake F or Lake E on the right-hand side of the slide, have some connection with the ice sheet and have got suspended sediments in them from the glaciers. The landscape actually gets surprisingly warm in Greenland. The lakes, not so much, but the land surface temperature in the height of summer across this part of Greenland can be surprisingly warm, as you see, up at 30 degrees. And that's only kilometers away from an ice sheet that's pegged at 0 degrees. So it's really quite an interesting landscape. We were able to look at the typical annual cycle of these lakes in terms of temperature. This turns out to be quite important. It had been widely assumed that lakes next to the ice sheet never really increased in temperature above 1 degree or so. That's very far from being the case. They can reach several degrees, even 10 degrees over time, and that can have a feedback effect on the ice sheet. And we've got a project with colleagues at York and Leeds and Bangor looking at that possibility ongoing. Also able to look at the season and the length of open water on these lakes, which are frozen during the winter and only open in the summer. The seasonal length of open water is changing over time, as you might expect, in interaction with the climate. And then we were also able to look at all the lakes in that landscape using Landsat and characterize the maximum temperature observed across the lakes in the course of the summers to see what it depended on, and that is shown here. You can see dependencies like you expect. As the albedo goes up, less sunlight's coming in, and therefore the energy doesn't take the temperature as high in the course of the summer. So that's the last of my case studies. Four very different case studies. I guess we'll move straight on to Abigail's presentation, and then there might be questions at the very end, so I'll hang on.
So we can take a few questions because I'm going to put Abby's presentation on from our computer.
Right. Okay. So
right.
If someone can relay any questions whilst you're doing that, that'd be fine. You want me to? Do I need to stop?
In a second. Any questions so far? We can do a few short questions at the end as well. Okay. Is that yours now? Okay, very nice. It's still not sharing. I should be able to share now. Please can't share. And please let us know if you can see the presentation.
Yep.
Okay. So the floor is yours, Abby.
Okay, so mine's not going to be as long as Chris's. So it will be a really niche whistle-stop tour, but I just think I'll cover all the basics, and then I'll show you the article that I've written that actually goes into everything I'm going to talk about, that's really in depth, that's actually on the SIG website. So you can get all the links and all the data availability and all more in-depth things on there as well. So, oh, I'm on the wrong one. There we go. This is a great start, isn't it? There we go. Okay, so a very quick overline. So we'll be looking at the significance of ice and snow analysis. How is the cryosphere in general changing? The thermal signatures of ice and snow, and then data sets relating to that as well, and then a quick study on the Peterman Glacier ice shelf. I always use this one purely because I did this was my master's thesis presentation, so it's easiest for me to explain. Okay, so a quick overview is that ice and snow plays really crucial roles in various natural systems in human activities. So the constituents of the cryosphere is anything that's snow cover, sea ice, freshwater ice, ice masses, so ice shelves and ice sheets. But you get the extremities, so the polar regions, which are the Arctic and Antarctic. And then the advancement of remote sensing technology and techniques offers advantages to further understanding and large-scale changes in these regions. And essentially, the cryosphere, or mainly the poles, actually act as the world's refrigerators. And most people do know that, but the significance of that I will explain along, and how we can monitor that with thermal data. So a quick overview is how the cryosphere is changing, and it's mainly due to positive feedback mechanisms, usually, oh, you've got the thing in the way, but it's to do with albedo effects mainly, and positive feedback mechanisms with changing human activities. So the really high reflectivity, or the albedo, of ice and snow cools polar regions and areas of the cryosphere. And that helps to regulate Earth's global temperature, especially the disparities between the heating of the equator and then the cooling at the poles. So a lot of changes have happened. So we have, with increased global warming, and greenhouse gas emissions, we actually have Arctic amplification, especially in obviously the Arctic, where the Arctic's warming up 4 times faster than the rest of the Earth. And that then reduces ice cover and snow cover, which then reduces the albedo, and that reduces the global cooling, and then that encourages more heating of the Earth, and so on as a positive feedback mechanism. And then again, human influence is a big part of this. 2 of the major regions that are reductions in albedo are the Greenland ice sheet as a whole and the Ross ice shelf in Antarctica. So the darkening of these surfaces due to melting is accelerating these ice losses. So a quick overview of thermal signatures. So on the graph on the left compares the emissivity of solid ice, liquid, seawater, and different types of snow across different thermal wavelengths. However, in general, if you group snow and ice, it's very close to that of water in general. There's a much higher emissivity to the liquid seawater, especially at longer wavelengths, whilst coarser granular snow exhibits the highest emissivity among all of the snow types. Especially around 11 microns. This is really important in remote sensing applications. It helps differentiate between ice, snow, and liquid. You can't necessarily see the difference on a granular level in infrared, but when you look at microwave data, you actually can. So the impact of this is that the changing thermal signatures of ice and snow and the changes in those phases will then affect the ice surface temperatures of that region. So as it melts, obviously the thermal signature changes, and then that will affect the albedo, and then the local microclimates. And then we are looking into, I actually am studying land surface temperature, part of my PhD, but my specialities are in the poles. So the main thermal signature we can look at are ice surface temperatures, which is just another derivative of land surface temperature. So again, that theory states that just all the objects emit thermal radiation based on their temperature, with surface features like ice, snow, melt ponds, proglacier lakes, superglacial lakes, all at different wavelengths, and they can all be determined by their temperature, which we can monitor from satellites in space. So ice surface temperatures will emit in the mid-wave and thermal infrared. We mainly use the thermal infrared. Due to as was explained by Agnieszka in Monday or Tuesdays, due to the wavelengths that we can actually accurately see through the atmosphere. Unfortunately, the poles especially are really cloudy places, so thermal data can be really, really limited, but there are ways in which we can merge with other data sets and actually use other types of data sets complementary to this. And then again, this just reinforces as surface temperatures are rising and the ice and snow is melting or responding more, it's actually the mass balance is reducing. So as more melting in the summer, and even though winters are warmer, the accumulation of snow is actually reduced. So we're in a deficit. And then this melting exposes low albedo surfaces. And again, it's that whole positive feedback mechanism that's happening. And it's really critical to changing levels of ice and snow in all over the cryosphere, but again, especially in the Arctic. So I'm going to talk about 2 other complementary types of data sets. So as satellite imaging has advanced in accurately measuring snow accumulation, depth, water equivalent, albedo, producing high precision snow cover maps generally outperform things like ground surveys and aerial photography. So snow cover maps don't directly use thermal data like land surface temperatures that we just talked about, but the thermal data can complement them by revealing links in the snow cover and the surface temperatures, and that helps us analyze the seasonal changes and the feedback mechanisms. Understanding the changes in snow cover can help support climate studies, hydrology, water resources in the local areas, hazard monitoring, and then resource management as well. Whereas thermal data can complement these maps and shows the links to the changes, and you're able to tell a story, especially at broader spatial resolutions over large areas. And then we can always also use thermal remote sensing when detecting changes in ice and snow temperatures to monitor melt and assess the extents as well. Things like sea ice and ice shelves. Over large ice sheets of Greenland and Antarctica, melting is one of the largest drivers for mass loss, either through direct runoff or in the impact of changing ice dynamics, which I'll kind of give an example on in the case study. But we can use thermal remote sensing alongside other data sets such as snow cover and ice extent to again paint another picture. So surface melt, snow melt reduces reflectivity, and then melting at the base of ice shelves in glaciers can cause accelerated mass loss, which then causes sea level rise. And then we can also look at thermal data on ice ponds and ice and sea ice decline, and we can again kind of paint a story along with other types of thermal data. So I'll take an explanation. So we're going to look at the Petermann Glacier ice shelf in Greenland. So an ice shelf is essentially, for those who don't know, is essentially a floating platform. So a glacier is a marine terminating glacier meets the ocean and continues to flow out, and you have a long tongue of ice, as you can see in the left. So the Petermann Glacier is in the northwest coast of Greenland, and there were two major calving events, as you can see on the right-hand side, one in 2010 and one in 2012, and we're going to look at the changes, why this happens so fast and why this is important, and how we can look at the data using thermal infrared. So I have two, well, I've got a GIF and an image actually. So on the left, you can see the change. This was the first major change in the summer of 2010, and the ice shelf reduced by almost 17,000 meters, and actually it caused an ice speed increase of 282 meters per year. And then another fracture turned into an iceberg carving on the right, which is 2012, and that reduced the terminus by another 8,430 meters and increased this ice flow speed of 262 meters per year. For reference, I don't know if anyone can see down there, but in 1988, the ice speed was 148.8 meters per year. So it's a significant increase. And again, I'll explain why that happens later. But basically what we're looking at are two major calving events of an ice shelf into an iceberg out into the ocean. So I looked specifically into the climate drivers, even though I do study glaciology. I'm mainly a climate scientist. So we all know about Arctic amplification, as I described, but the main key area for this was rising surface temperatures. So on the bottom, we have land surface temperature, and bottom left, sorry, and the bottom right, we have sea surface temperature. And as you can see in both regions between 2010 and 2012, there were large jumps in these temperatures. Now, everyone would say, oh, that's really, really a large jump. Yes, this mainly happened due to a natural change in climate. So mainly influences in sea surface pressure and surface and atmospheric circulation. So things as the North Atlantic Oscillation and something called the Greenland Blocking Index, which is basically a change in pressure and geopotential height over Greenland. However, this doesn't usually cause an iceberg carving so frequently, and this has been linked to general rising temperatures over the last 2 to 5 decades, which is causing these natural phenomena to happen stronger and more frequently, and then that causes things like reduction in glaciers and iceberg carving. So why do we care? So even though carving of an ice shelf is a very natural thing to happen, it should happen every summer, and then the glacier will gain mass again in the winter. When an iceberg carves off a marine terminating glacier, it actually causes speed up in glacier melt and discharge into the ocean. So as more icebergs are being carved off, more water and more ice flow increase into the ocean, and since winters are getting warmer, it's really hard for that resistance to come back, and this is known as buttressing. So the ice shelf essentially acts like a plug hole to the main parent glacier, and obviously if you pull out a plug hole, the water's going to go. So when this iceberg gets carved due to increasing land surface temperatures, increasing sea surface temperatures, then that's a really big problem for all outlet glaciers. And this is why the Greenland ice sheet is one of the largest contributors to sea level rise in the world, because of rising temperatures in the ocean and atmosphere, which are causing increased melt at the outlet glaciers. So that was the Whirlwind Stop tour. I'm happy to take any questions and talk any further. I know we're under a lot of time constraints, but the general overview is that we can use thermal data to look at different types of ice shelves and ice sheets and lakes and glaciers all over the world, and we can interact that with other data such as snow extent and sea ice extent and paint a picture of the patterns and trends that are happening, and we can relate that to the feedback mechanisms which are causing further decline. And that's really important for keeping the globe cool, really. So, yeah, thank you.
Anybody have any questions to Chris or Abby? Sorry. Excellent.
So thank you for the presentation. Yeah, it's for you actually, the question. So the data you showed for the Greenland, for example, are they more all from MODIS, I mean for satellite, or you tried also other sources? Because I'm testing some like MODIS Landsat or other products from satellites applied to ice and snow, and the results are not always really like similar.
Yeah.
We have strong differences in the results. So we're trying honestly to see what's the issue, which the best. I don't know, honestly.
Yeah. I mean, I think it completely depends on where you're looking. If you're looking at, the Arctic as a whole or sea ice in extent, a 1 kilometer aquamodis is quite good. But if you're looking at small lakes and small glaciers, it's quite difficult. It kind of segues really well onto this is everything I just spoke about, you can get on the SIG website. And if you go, I kind of just explain everything that I've talked about, and data availability, which I didn't cover, is actually right at the bottom if I can find it. And I specifically looked at MODIS because that's what my PhD is in. And that's obviously niche to my area, but there's other ones like VIRS, SLSTR, but again, thermal have big issues, especially in the poles with cloud cover. The LST-CCI have a infrared merge product, which kind of makes a much larger temporal range. I'm actually working on a merge product merging infrared and microwave, which then will kind of give us an all sky product. So again, it's really niche to your area. If you're looking at more of a climate stance like I have, or a larger effect on say Greenland or Antarctica, then I would say, but I am biased, I would say like MODIS, Aquamodis, TerraModis, SLSTR, things like that would be your best bet. But I would look at ECCCI data sets. I would look online about all of these types of data sets that you can assess. It just completely depends on where you're looking at and what resolution, and also how much data you need.
Yeah. Okay, thank you.
Are there any other questions from the audience? I would have one to Chris, if Chris, you can still hear us.
Yes.
Excellent. So my question would be, what is the maximum deviation of emissivity in sea surface temperature that we can expect?
Emissivity doesn't vary more than a couple of percent.
Okay.
In the 11 and 12 micrometer window, that is.
All right. Thank you. Okay. Any other questions? Last questions? We will leave the website open so you can look at it later. Thank you again, Chris and Abby.